Hi everyone, so right now we are entering section 2 for chapter 3. So section 2 is on electromotive force and internal resistances. So this is chapter 3, this is section 2, and the title is on electromotive force and internal resistance. Okay, we'll go through these two terms later in the following in the following explanation, but just to give you a heads up, electromotive force is not the force. Okay, that's one thing weird about physics. Sometimes we have really bad names for things. So electromotive force later will not be a force, so I'm just giving you a heads up in case you think that there'll be Newton involved in this particular video. No, there'll be no Newton involved. Okay, so to understand electromotive force and internal resistance, let's bring back a bit of our understanding of a simple circuit first. Okay, so right now I'm going to talk to you about an ideal circuit. Ideal simple circuit. Okay, so this is an ideal circuit. What will happen is you will still have basic three components in which you have your battery. Okay, your battery is connected to a resistor. So let's say today over here you maybe might plug in a switch here. Okay, and it's closed right now, and you have your basic circuit right now. This is an ideal circuit which consists of a battery, a resistor, and connecting wires connecting between them. Okay, later on we'll also spend some time to study about a realistic circuit, which is a circuit that you usually encounter in real life. So we'll discuss first the ideal circuit, then afterwards we'll move on to talk about a real circuit. Okay, so in an ideal circuit, our charge will be moving throughout the circuit, like round and round and round and round. So before this we already discussed already, the battery acts as an energy supplier, whereas the resistor here will be taking up the energy to be dissipated as heat, right? So let's try to investigate a journey of a charge. Okay, let's say I'm focusing on a 1 coulomb charge, which will be going around the circuit. Okay, so it will be going around from the inside of the circuit. Okay, the inside of the circuit, that's labeled in yellow. So this is the inside of the circuit that it will be going through. Then afterwards it's going to continue its journey. Let's do it in green. The journey outside the circuit. Then it will pass through the resistor. Let's do it in orange. Then afterwards you continue its journey back to the negative terminal. Okay, so I'm going to focus on the path that will be traveled by a 1 coulomb of charge when it's moving inside the circuit right now. Okay, so I'm going to break it open into a line to show the whole path from start to end. Of course, we know it goes around in circles and circles and circles, but let's start from one point and come back to the exact same point and see what happens to the energy exchanges throughout the journey. So I'm going to open up this circuit and sort of draw it something like this. I'm going to draw a negative terminal followed by a positive terminal. And this will be the path went through by the charge. At some point you encounter the resistor, then you continue its journey until you reach the end over here. Okay, so if I want to label it using the highlighter, it's similar. This is the initial path inside the battery to be supplied with some energy first. Then afterwards you continue your journey outside the battery from the positive terminal towards the resistor. Then once you reach the resistor, you pass the energy to the resistor. Then you continue your journey until you reach back to the negative terminal. Okay, so this is the path I'm going to open up and explain about energy exchanges. But for now, let's just assume that this battery here is a 6-volt battery, and this I think this is a 2 ohm. Is it 2 ohm? 4 times 2.5 current. This is a 2 ohm. This is a 2 ohm resistor. Okay, so this is an ideal circuit that I'm going to investigate right now. So let's try to study what's happening over here. Okay, so we have a 1 coulomb charge. So let's say this 1 coulomb charge will be traveling in circles and circles, but let's just set the negative terminal as a starting position. Then we'll be going through the battery, coming out from the battery, and go through this journey until it arrives back at the negative terminal. So this is a journey went through by 1 coulomb of charge, and let's try to study what is the amount of energy exchanges that happen throughout the journey. Okay, we know that this is a 6-volt battery. Based on our understandings of what is volt is joule per coulomb. That means that if I have a 6-volt potential difference, when 1 coulomb of charge pass through it, they will involve a 6 joule kind of energy exchange. If it's a resistor, the resistor receives 6 joule. If it's a battery, the battery will supply 6 joule for every coulomb of charge that pass through it. So right now, this is 1 coulomb of charge passing through the battery. We know that this battery is a 6-volt battery. Okay, it's a 6-volt battery. So what happened is it will be supplied by 6 joule of energy through this process. So add 6 joule energy for every 1 coulomb of charge that passed through. So we know that initially it comes back at the negative terminal with 0 joule energy. That means that once it exits the battery, it receives 6 joule energy. So now it exits the battery with 6 joule energy. Okay, so if you want to write some description to what's happening over here, we can say every 1 coulomb of charge is supplied with 6 joule of energy by the battery. Okay, so this is what happened when the 1 coulomb of charge passed through the battery. Okay, so once it come out from the battery, it has 6 joule energy. It will continue to travel over here. So during this travel across the wire over here, because the wire is made of, like, we assume it to be a perfect conductor, so it will not consume energy at all for the charges to pass through it. So we assume that there is no exchanges over here. Maybe I should be a bit clearer. I'll write the summation and subtraction at the bottom. So this is plus 6. But right now, there's no energy involved over here when it go through the green section. So arrive at this position over here also with 6 joule energy. Okay, there's no exchanges at the wire because we assume it's a perfect conductor. You don't need to use any energy to pass through. So the energy that is initially possessed by the positive 1 coulomb charge will still remain when it arrives at the entrance of the resistor, let's say. Okay, but right now we know that this is a 2 ohm resistor. So if this is a 2 ohm resistor, what happened is that's the only component available in this circuit over here, right? We know that the battery acts as an energy supplier, but that energy has to be supplied somewhere. And since if we look through this circuit, there's only one component available in the circuit, in the external circuit outside the battery. So you know that all energy that is being given by the battery over here will have to be fully given to the resistor over here, because there's no other components that can receive energy anymore. So that total 6 joule energy that is brought by the 1 coulomb charge must all be given to this 2 ohm resistor. Okay, so that means by this resistor here will be receiving all 6 joule of energy. Okay, so since the resistor will be accepting that 6 joule energy, we expect that the charge will lose 6 joule energy. The charge lose all 6 joule energy, so you exit the resistor with 0 joule of energy. So we can say what happened here is every 1 coulomb of charge is supplying 6 joule of energy to the resistor. Okay, so that is what happened. So you end up with no energy at all. So that charge being 0 energy right now will come back to the negative terminal of the battery. Okay, don't worry that because it's 0 joule you cannot move, you can still move. It's just that the motion, because it's a perfect conductor, you don't need any energy to pass through this section. So initially, even though you have 0 joule at this point, you can still sail through smoothly and you reach here, no problem with it. Okay, so this is what we talk about when we talk about the energy exchange in an ideal circuit. You have the battery being the power supplier or the energy supplier, the resistor being the energy user or the energy receiver. Okay, but what happened is today, let's say if you want to look at a more realistic kind of circuit, a more realistic kind of circuit will probably look something like this. Okay, you still have your battery, don't worry about it. But this battery here, there's something called an internal resistance inside the battery. Okay, so things are not so easy right now. Inside the battery, there will be internal resistance. Why is the internal resistance? I will explain to you later, but for now, this is just not your ideal battery anymore. Okay, but this is still the same battery, but in a realistic case, this battery actually poses some internal resistance. Okay, so if we connect it to a resistor like just now, you see something different will happen in a more realistic circuit. Again, this is the same battery, but I'm going to write it as, so I'm going to write it as 6 volt over here, I'm going to write it as 2 ohm over here. But in a realistic case, you have to consider there's resistance inside the battery, so things will be a bit different right now. Okay, again, I'm going to study what happens to a charge that goes from this negative terminal, go through this circle until you reach back to the negative terminal. Okay, I should have drawn this as well. This is a journey that I'm investigating right now. Okay, so if I want to expand it out and put it into a straight line, then again it will start from the negative terminal, then you go to the positive terminal. But instead of drawing this internal resistance outside the battery, let me squeeze it in between the terminals, because this resistance is actually inside the battery, right? So I draw it inside the battery like this. Okay, so outside of that, you will still continue your journey. You still see your resistor. After you go through a resistor, you still reach the negative terminal. Okay, nothing much has changed except for what happens inside the battery. So again, let me label what happened. This is your yellow section. Coming out from the battery, you have your green section. Hey, sorry, green not supposed to continue until here. So much drawing. Green here, green here. Afterwards, it'll be orange, orange here. Then it'll be blue down the road. Okay, so this is the kind of circuit that you should be expecting right now. So if I pull it open into a straight line to focus on the path traveled, then I'll probably start with a yellow section inside the battery. Then once you exit the battery, then you have a green section. Then afterwards, you have the orange section, followed by the blue section. Okay, so again, we're going to investigate what's happening here. So let's start again. So again, you are going to study the journey of a 1 coulomb charge. From the negative terminal of the battery, go through the battery, when outside the battery, go through the whole external circuit until it comes back to the negative terminal. Okay, so again, you start with 0 joule of energy. But passing through the battery allows you to obtain that 6 joule of energy, allowing you to come out with 6 joule energy. That's what we discussed earlier. But things are not so straightforward actually. Because what happens over here, even though the battery did his job by supplying energy to the charge, to pass through the battery itself also requires some energy. Okay, so let me write down what's happening over here. There's two things happening at the same time actually. So you know that every 1 coulomb of charge is supplied with 6 joule energy from the battery. But at the same time, we know that battery inside there's chemicals inside. If it's a nickel cadmium battery, then there'll be nickel and cadmium. Lithium ion, then probably there's lithium inside. It depends on what kind of battery you're talking about. But all these kind of battery, inside there is some chemicals. Okay, so if you think about it, for the electron to be going through all those battery material, those battery material itself also pose some resistance to the charge. It means by all these chemicals inside a battery, they are not perfect conductor either. So if they are not perfect conductor, they will take up a bit of energy for the charge to pass through the battery actually. So for the charge, 1 coulomb charge to pass through a battery, actually there will be some energy that needs to be used in order to get through the battery. So you actually use up some amount of energy. So I'm going to write as minus X in order to get through the battery material. So what's happening here is not just this one thing. You just know that every 1 coulomb of charge is using X joule of energy to pass through the battery material. Okay, so the battery, even though from idealistic world, it is as if the battery is like a full philanthropist. His job is only to give, his or her job is actually only to give out energy. I am a 1.5 volt battery, then my job is to give every 1 coulomb of charge that pass through me, I will give 1.5 joule energy. His thing seems to be very beautiful, like he's a full blown like philanthropist. But in a realistic case, right, just for the charge to pass through the battery itself, for the charge to get from the negative terminal to the positive terminal, that process itself actually takes up some energy as well. So even though, let's say for this case, the battery say, I'm going to give you 6 joule energy, but at the same time you say, give me back 1 joule, because it's difficult to get through here, right? Okay, you need to use up some energy, so I'll take back that 1 joule. Okay, so it's not that ideal anymore. I'm not giving, the energy that I give you is not fully available to be used outside. Okay, just now in the initial case when we talk about ideal circuit, the whole 6 joule energy supplied by the battery is fully available for the external circuit to use. But right now, even though the battery is indeed supplying 6 joule energy, but not all 6 joule energy is available for the outside, because some amount will be actually used even before the charge has already exited the battery, because to get through all those battery materials requires some energy as well. So the amount of energy used, I'm going to use it right as X right now. So once you exit the battery, the amount of energy you have will be 6 minus X joule of energy. okay, which I'm not sure what's the value right now. Okay, so going through the connecting wires, nothing will happen. There will be no loss of energy to the charges, so you still arrive outside the resistor with 6 minus x joule energy as well. Okay, but you know that this is the only component that can take up the energy throughout the whole external circuit, right? When I say external, it means outside the battery. The whole external circuit, there's only one resistor to take up the energy. That means that the whole 6 minus x over here will be passed to the resistor over here. So that's why you the charge will experience a net minus 6 minus x amount of energy, so resulting it to be left with 0 joule energy coming back to the negative terminal. Okay, so we should also write down what's happening here at the 2 ohm resistor. So right at the 2 ohm resistor, what's happening here is that every 1 coulomb of charge is supplying 6 minus x joule of energy. To the resistor. Okay, if I want to be a bit more general, right? Okay, let's say if today I have more than one resistor, the idea is that to the resistor is actually to the external circuit. Okay, so anything inside the external circuit, if there's 2 resistors, it will give out the 6 joule to the 2 resistor. If there's 4 resistors, then it will give out to all 4 resistors. So it's actually given to the external circuit. Okay, so it'll be left with 0 joule of energy. Okay, but I should probably make a bit of range changes over here. This is indeed a 6-volt battery, but I should write it as it's a 6-volt battery with a certain number ohm internal resistance. Okay, it's not the kind of ideal battery that you have. It's a realistic battery with a certain amount internal resistance. Okay, so this is how I would think about an ideal circuit and a real circuit. So right now, focusing on this real circuit over here, I want to explain about the energy transfer that involved. Okay, so what we have over here is actually a kind of energy exchange which you need to figure out the equation. Okay, give me a second to double check on the equation arrangement. Because I'm worried that I'm writing it in a different way from your syllabus. Okay. So our focus when we are discussing this real circuit here is always what's available for the outside. Okay, what's happening inside the battery is the least of our focus. Our focus is actually what's happening outside the battery. So we are always trying to know how much energy is actually available for the external circuit. So if you want to quantify it, how much is the energy available for the external circuit? I have to take the energy supplied by the battery minus the amount of energy that is being used, right? Because after using that small amount of energy to get through a battery, only the remainder can be used for the external circuit. So in order to find what's available for the external circuit, I have to take what's being supplied by the battery minus out what's being used to pass through the battery. Only that remainder will be equals to what's available for the external circuit. So saying that, I will be able to construct an equation that sort of looks something like this. Sorry, I have to refer to the notes in my writing so that I don't make any, so it makes more sense. Okay, so we know that this is the energy supplied every 1 coulomb of charge passing through the battery if you take the energy, we minus out the energy used by every 1 coulomb of charge to pass through the battery material. Okay, as I said just now, battery, they have different materials inside. Those materials are not perfect conductors, so they need some energy for the charge to pass through. They take up some energy to pass through the battery material. Then only the rest of that can be available for the external circuit. Energy made available by every 1 coulomb of charge to the external circuit. Okay, so this is the energy given by the battery. Some energy is being taken up just to get through the battery, so the remainder of it will be available for the external circuit. Okay, so if you want to put it into symbol, and that's where the mathematics matters right now. If you want to put it into symbol, then the symbol will sort of looks like this. Okay, the energy supplied to every 1 coulomb of charge passing through is called the electromotive force. Okay, this is the important part right now. This is the electromotive force. And electromotive force has a symbol of epsilon. Okay, then minus something. Okay, this energy used to get through a battery material is just the voltage drop. I call it potential drop, sorry. Just trying to be accurate with my wording. This is the potential drop in the battery. Why is there a drop? Because you want to use that drop to get through the battery material. Okay, I'm going to leave the symbol blank first, later I'll fill it in. And lastly, this is equals to the what's available for the external circuit. What's available for the external circuit, there's a name to it. The name is called terminal voltage. And the symbol of it is V terminal. Okay, I hope all of you can notice that this is energy to every 1 coulomb, energy by every 1 coulomb. So energy by every 1 coulomb. This is joule per coulomb. So if this is joule per coulomb, based on our understanding just now, joule per coulomb, we're talking about voltage over here. So this electromotive force is actually not a force even, it's actually a voltage. So the unit for this electromotive force, it's a voltage, it's volt. Okay, and of course terminal voltage, as the name itself implies, it is a voltage itself, so the unit will also be volt. And lastly, this potential drop to internal resistance will have to be the same unit as well, because we are talking about wanting this equation to be dimensionally homogeneous, right? So all the terms inside, if you are adding them up or you are subtracting them, you need them to have the same unit. So if this is volt, then this must be volt as well. So this potential drop, as the name implies, is potential, so the unit must be volt, right? But what kind of symbol do we write here? Well, we know from our discussion just now, there's a potential drop due to the battery material, and we can say the battery material itself is not a perfect conductor, so it has some kind of resistance, right? So we are going to label this resistance inside the battery with a small r, and that small r here represents internal resistance. So this is small r over here represent internal resistance. So if we know that that's the internal resistance, then how much voltage is dropped due to the internal resistance? Well, just treat like any other resistor out there. If any other resistor, like let's say this particular resistor, if I want to know the voltage, how do I know the voltage? I just take the resistance, multiply by the current flowing through it, then I can know the voltage across it, right? So if I want to find the voltage drop or the potential drop across the battery, I just need to take this R multiplied by the current that is flowing through this circuit right now. So that means by this thing, we are going to explain it in terms of I multiplied by R instead. Okay, of course you might think that why not just write it as V internal resistance, the drop due to internal resistance. Well, it's just that we don't write it that way. You can write it that way, it's still logical, but we don't really give it a certain symbol, we just leave it as IR, where R is small because it represents internal resistance. Okay. So this is just your normal definition of resistance, where R is equal to V over I. So shift it around, V equals to IR. Okay, but this one is the internal resistance, so the unit will be ohm. Okay, continuing on that, you will see that this equation can be manipulated in various ways. Some bring this IR to the right hand side. So if you bring it to the right hand side, you see the equation become epsilon is equals to IR plus V terminal. So this is a valid way of writing it as well. So if you want to understand it in terms of words, this is the energy supplied by battery. So that energy being supplied by the battery will be used for two purposes. One is to get through the battery itself. One is to get through the circuit outside the battery. So this is inside the battery, how much is used. Outside the battery, how much is used. Okay, so if you write it like this, we can further manipulate the equation by knowing that, okay, this one still remain the same, this one still remain the same, but we know that V terminal here is what's available for the external circuit, right? So for an external circuit, there's this resistance available. So if we know this resistance, we can actually find what's available for the external circuit by using the same V is equals to IR. So just now it's for internal resistance. So right now this is for external circuit, right? So this will be external resistance now. So this one we can expand it to become IR. Okay, so this one is resistance. You can call it effective resistance. It's a combination of resistance at the external circuit. Okay, so we are not taking in what's inside the battery. We are only taking in what's outside the battery. Okay, sometimes you can see people write REFF as well, just to represent that it's a combination, because it's not necessarily one resistor, right? It can be two resistor in series followed by two resistor in parallel. So what you need to do is just combine them all, then that combination of resistance will be plugged in here as effective resistance at the external circuit. Okay, so if you look at this path over here, I believe all of you can see that this is only one path available, right? There's only one path available for the charges to flow. So one path available for the charges to flow. So that means if there's 1 coulomb of charge passing through the battery, later on there will also be 1 coulomb of charge passing through the battery. Okay, so if I'm telling you today that let's say right now there's 2 coulomb of charge passing through per second through the battery. So every second you see 2 coulomb of charge coming out from the battery. So that also means by you have 2 coulomb of charge passing through the resistor every second, then there will be 2 coulomb of charge reaching the negative terminal every second. Everywhere along this path should have the same current, because you can think of current as like soldier marching actually. So you can think of there's a bunch of soldiers lining up inside this wire over here. So if the soldiers at the back move to the front by 5 steps, the soldier at the front of it, we also need to move 5 steps. The soldier even in front of it, we have to move 5 steps. The soldier even in front, you have to move 5 steps. Everyone will move by the same pace forward. So if I say that at this checkpoint, I see 5 soldiers passing through every second, that means by at this checkpoint, there will also be 5 soldiers passing through. At this checkpoint, I also see 5 soldiers passing through, because they are all marching together. Okay, so using the analogy, you can sort of understand that why this whole path here is supposed to have the same current. So because the same current passes through the battery and the same current goes outside the battery, you'll know that this I for the internal resistance and the I for the external resistance should be the same I, because they belong to the one single same path. That's why this I is the same. We are able to factorize it together. So if you factorize it together, the equation becomes epsilon is equals to I R plus R. So this is internal, this is external, right? So together, small I and big R will be the effective resistance of the whole circuit. So it doesn't care whether you're internal or external, of the whole circuit, that's the effective resistance. Okay, so this is a few ways that we can manipulate this equation over here. So the important things that I usually use for your syllabus, it's you need to know this relationship. This is given in your equation sheet, but you just need to know it as energy supplied by the battery, some being used up by the battery itself, the rest is being used for the external circuit. Then usually we can also manipulate it using manipulate into this form. This form is also very useful as well. Okay. And lastly, another thing that is actually quite useful as well is this part, where V terminal is actually equals to IR. Okay, so by knowing these 3 equations, you should be able to manipulate your equation well to solve any question regarding chapter 3 section 2. Okay, so before we go, let me fill in some values here to let you know what are values that are supposed to be not changing, what values can be changed. Okay, we are not able to manipulate anything that is inside the battery. The battery is well packaged already, right? So the material inside will still be the same material. When we buy the battery is always labeled with a certain voltage. Let's say 1.5 volt battery for an AA battery. That 1.5 is referring to the energy that can be supplied to every 1 coulomb of charge. So this is what you can see outside the battery. Okay. This is what's on the packaging. So when every time I buy a battery, if it says 9 volt, then that's the electromotive force. So we know that that value must be constant. It's impossible that when you're using the batteries, at a certain point you see that the 9 volt suddenly change number to 8 and suddenly change number to 7. No, the battery, when I say it's 9 volt battery, that means by it is fixed already. The electromotive force is fixed. So what's on the packaging means by this thing must be constant. Okay, in this case, I mentioned this is a 6 volt battery, right? That means this 6 volt over here is the epsilon. So this epsilon is constant. Okay, afterwards, we also know that inside the battery there's chemical. So the chemical, it's that chemical. You cannot open up the battery to see to change the chemical. That means by the amount of resistance that the battery material poses will be constant. Okay, unless you change the battery to another kind of battery, you change the material inside, then internal resistance might be different. But as long as you do nothing inside the battery, it will still be the same internal resistance. So this R itself should also be constant as well. This small r over here should also be constant. Okay, so in that case, let's say today I'm giving you an example where this R is equals to 0.4. Okay, if I put R to be equals to 0.4, then what you can do is you can plug in all this information here to determine the current using this equation. So if I plug in 6 over here, and I plug in 0.4 as small r, I plug in 2 as the big R. If I go through the calculation, it will be 6 divided by 2.4, right? 6 divided by 2.4, you get 2.5. That means by the current will be equals to 2.5. Okay, so there will be a current of 2.5 flowing through the circuit. Okay, initially if you look at an ideal circuit, this is V is equals to IR, you get that V is 6, R is 2. Then for ideal circuit, you see that the current is actually less. The current is actually more for an ideal circuit. The current is 3 ampere. But because it's a real circuit, right now you see that the current has actually decreased, okay, due to the internal resistance. Okay, so for this particular circuit, you can continue and say that because the R is also equals to 2 ohm, then your current is equals to 2.5. Okay, just want to clarify carefully, this thing here should be constant. Because it's in the battery, you cannot do anything about it. But this thing here, which is R and I, it can change because it's something outside the battery. Okay, let's say today you don't want to install a 2 ohm resistor, you can change it to a 5 ohm resistor. So if you change it to a 5 ohm resistor, then it will be 0.4 plus 5. Then you get a new different current, right? So the R and the I are values that can change. Okay, so when you're dealing with questions involving electromotive force and internal resistance, make sure you know that the epsilon and the R, unless you're changing something inside the battery, should always be constant. Whereas this big R and I here can change according to what resistor you put in. The greater the resistor you put in, the greater your R plus R will be, then you further reduce your current flowing through. So if you reduce your current flowing through, you adjust the proportion of how much is used inside the battery and how much is used outside the battery. Okay, so this thing you can further practice on it using a few exercises, and I believe that's all that I want to mention from here. Oh, okay, actually I can do more. Okay, if I want to know how much potential drop is at the internal resistance, right? Okay, I already know that this is 0.4. Let me fill it in. Oh, sorry. Okay, just now I write 6 volt battery with how much ohm of internal resistance, right? So that how much ohm is 0.4, right? Okay, so I can fill in the number is 0.4. So if I know the number is 0.4, then 0.4 multiplied by 2.5 allows me to know how much is the drop. Okay, I can find IR is equals to 2.5, right? Just now we say the current is 2.5 multiplied by the resistance. So this is equivalent to 1 volt, right? That means by this potential drop across the internal resistance is actually 1. So we can change this number to become -1. So this one will become 1. That's why this one will become 1. So it become 1. So effectively, there's only 5 joule energy that can be supplied outside. Okay, so the whole story right now becomes like this. The battery supplies 6 joule energy to every 1 coulomb of charge passing through it. But at the same time, the charges, after receiving the 6 joule energy, will also use up 1 joule of the energy to go through the battery material. So you receive 6, but use up 1. So you come out here with only 5 joule energy available out for the outside, for the external circuit. So the charge will carry that 5 joule energy across the connecting wires until it arrives at the resistor. They will give up that all 5 joule energy, the rest, the remaining, after using up that 1 joule in the battery, the remaining 5 joule will be given to the resistor and be left with no energy at all once it reaches the negative terminal. Okay, so this is a more realistic picture right now compared to the ideal circuit where there's no energy loss due to the battery. Right now there's energy loss due to the battery, so not all the energy supplied by the battery can be used up in the resistor. Okay, so that's the description of an ideal circuit, comparing it to a real circuit. I hope you benefit from this video. And that wraps up my notes for section 2 actually. In the next video, we're going to section 3, which discuss series and parallel circuits for resistors. Thank you very much.